Okay. So the last section that we'll do for this exam is about exact differential equations. And to kind of understand what they are, we'll start with the simple equation y dx plus x dy equals 0. Which, by the way, is separable, right? And is also homogeneous. And is also equal to the derivative of the product of x and y. So if we took x, y, the product of that prime, we get exactly y dx plus x dy equal to 0. So in other words, to undo this derivative, we could say, you know what, let's integrate. So then we get xy equals c. So xy equals a constant is the solution for this differential equation. Now that's pretty nice and convenient if you can recognize that this equation was the derivative of some product. Because then if you recognize that, when you integrate, the derivative cancels the integral, and then you're just left with the integral of whatever's on the other side, and that's pretty easy. Okay? Let's see. What else? What other background do we need? Recall that if z equals f of xy, that the differential dz, so here's a little bit more Calc 3, was partial f partial x dx plus partial f partial y dy. Okay, and if this is equal to 0, then here's another way to describe the exact equation. Okay? So here's a differential equation. Okay. Let's just go straight to the definition, I think. A differential expression m of x, y, dx plus n of x, y, dy is an exact differential if it is the total differential of some function f of x, y. A differential equation of this form equal to 0 is called an exact equation if the left-hand side is an exact differential. So here's a question. Is 6xy dx plus 3x squared dy... Oh, is there a question?
Left-hand side.
Left-hand side. Sorry. Okay. So what do you think? Is 6xy dx plus 3x squared dy exact?
Yes.
How do you know?
Whoa. 6 makes it 6x.
Well, that's not fair.
How did you guys do that?
Well, he already knows. F of xy
I'm not looking at this section.
equals 3x squared y. So if we consider the function f of xy equals 3x squared y, then dz, or the total differential, would be partial x, which is 6xy dx, plus partial y, which is 3x squared dy.
Is there a way to like?
Yes, there is.
Because I will.
But yeah, it might be hard to kind of see that, so there's a nice convenient little test, which, move on, is, was that you that said?
Yes, exactly.
So what is that? What are you
Well,
comparing?
Since, partial f, partial x dx is the first part. The mixed first order partials have to be the same. So if you take first term partial y, it has to equal the second term partial x.
That is correct. Here's what he said, more formally. If we let m of xy and n of xy be continuous and have continuous first order partials, in a region R, we'll say A is less than X, less than B, and C less than or equal to Y, less than or equal to D, then m of xy dx plus n of xy dy equals 0 is exact if and only if, and you were saying that it was the partial y of the first one, right? So partial m partial y has to equal partial x of the second coefficient. So a nice quick way of knowing whether it's exact is nice. How to solve it, we'll talk about in a second. But if we go back to the example up here, partial y up here is 6x, partial x up here is also 6x. If they're equal, that's how we know it's exact. Okay?
Because that's like the second order. No.
Well, that's what he was saying, yeah.
Yeah.
It's from the mixed partials.
So, yeah.
It's also
It is very much like, say that again? Conservative
whatever that was.
vector fields, finding the potential function, yes. So if you guys remember how to find potential functions, guess what? You know how to solve this differential equation because the process is the same. Okay? Let's write that down. The solution is the analog of finding a potential function for a conservative vector field.
Well, isn't it just like checking to see if it's...
Well, first we check, which is kind of what we did, to see if it was conservative field or not, right? And if we knew it was conservative, then we knew that there was a way to find the potential function.
How long the way to find that is the same thing?
And here it's like, okay, well now we have an exact equation, so finding the potential function is similar, or if not the same, as finding the solution here. So let's look at an example now. So we have 9x squared y dx plus 3x cubed plus 1 dy equals 0. Let's see. So if I'm a differential equation student and I see this problem on an exam, at this point you probably have a checklist of things that you can look for, right?
Mm-hmm.
Can I separate? Is it homogeneous? And now the third one is this exact? Separation, let's see. You could separate, right? You get 9x squared over 3x cubed plus 1. Actually, that's pretty convenient because then the numerator is the derivative of the denominator, right? And then you just move the y over, not a big deal. So we could do it that way. Homogeneous, let's see. This is degree 3. So is this term, but that one's degree 0, so it's not homogeneous. Okay?
Well, could you explain what you just said?
About what?
The degree in...
The degree for this term is 3.
Why?
Because x squared and then y to the first, a quadratic times a linear, is cubic. And then here it's cubic, and here this has no degree. So it's not homogeneous, because all terms have to be the same. Right? So we could separate. We're not going to do it that way, though, because we need to learn how to solve exact equations. And let's just check now. If it's exact, that means partial m partial y, which is, in this case, 9x squared. That should equal partial n partial x, which is 9x squared. So it's separable, but it's also exact. Okay? So then the solution is the function f of xy equals c, which we can find by integrating either one of these guys. I'll take partial f partial x dx, because this term was the partial derivative of x, with respect to x. So if we go backwards and integrate, then we'll have an idea of what this function had to have been. So then we integrate 9x squared y dx, which gives us 3x cubed y plus some constant, which I'm going to call g of y. Remember that this constant could be in terms of y, right? Now, since we have partial f partial y, what's partial f partial y here? Partial f partial y has to be 3x cubed plus 1. That has to equal the partial derivative of this function with respect to y, which becomes 3x cubed plus g prime of y. So that means that 1 has to...
Oh, I see what you did.
You alright?
Yeah, I'm good.
Okay. So that means 1 has to be g prime of y, which if we integrate, tells us that y is g of y. And yeah, technically there's a constant over here. But in the end, it's going to be, we don't need to worry about it because we're just going to set it equal to the constant at the end. Okay, so you don't have to carry it. I'm okay if you forget that constant there. So now what's the solution? The solution, 3x cubed plus y, whoops, messed that up. 3x cubed times y plus y equals constant. That would be the solution. So this is the function to the, which is actually the potential function of the conservative vector field, if you want to think of it that way. Remember doing these? Those were fun. Yeah? No?
What's
If you had to like integrate f dot dr? No? Okay. I missed those problems. Okay. So that's essentially how to solve exact differential equations. I'm going to skip the next example because I don't want to do it. Let's talk about one more thing. This is like a precursor to the next, I don't know if it's exactly the next method that we do or the one after, but something that'll come back after the exam. Occasionally, it's possible to turn an ordinary differential equation into an exact equation by multiplying by what we call an integrating factor. We'll call it mu of xy. So that now mu of m of xy dx plus mu of n of xy dy equals 0 is exact. So the idea behind this concept is that without these there, maybe this differential equation is not exact, but if we multiply this differential equation by what we call an integrating factor, now this becomes an exact equation. Okay? Here's an example. So in this section, you will be, I believe, told what integrating factor you can possibly use if you choose to do it this way. So let's say we have negative y squared dx plus x squared plus xy dy equals 0. Just to review, because we have a test coming up.
Yeah.
Could we separate variables here? Why not?
Because if you were to try and divide by y squared to get rid of it over there, then you'd have, and you can't factor out x.
Yeah, if this would be great if it was x plus xy, right? Because then you can factor it out and then you can move it over. So it's not separable. Is it homogeneous?
Yeah.
So we could do it that way. All right. Right now, it's not exact because partial x here would be what? 0, and then partial y here is x. So it's not exact, okay?
Yeah.
Y the first one?
Yeah.
Oh, I'm sorry, I did that backwards. Partial y, yes, is negative 2y. Partial y here, or partial x here would be 2x plus y. Either way, it doesn't work. Okay. So you could use mu of xy equals 1 over x squared y to turn this into an exact equation. So you're going to be given this, and then your job is just to go ahead and multiply this whole equation by that and see what happens. So what do I get when I do that?
Negative 1 over x squared y. What? Yeah, you're right.
So minus y over x squared dx plus 1 over y plus 1 over x dy. And now partial m partial y, let's make sure I don't do that wrong this time, would be
Negative 1 over x squared.
negative 1 over x squared. Partial n partial x is exactly the same, right? So this is now an exact equation. We have 5 minutes. It won't take that long, so let's solve it.
So let's say it didn't work.
It will, for these, yeah. Because right now they'll tell you what integrating factor to use. If it doesn't work, that means you probably multiplied wrong.
Okay.
Yeah. Okay, so the solution we can find by taking, let's just take this coefficient here, minus y over x squared dx. That would become positive y over x plus a constant g of y. And then since partial f, partial y, let's see, what is that? It'll be 1 over x plus g prime of y. We're going to set that equal to the partial derivative.
Wait, is partial and partial y of the first or second?
Well, this is partial x and that's partial y. So I started with partial x, integrated it, so now I have what is a function of x and y, right? And now I'm taking the partial derivative of this function with respect to y and comparing it to the coefficient of dy, which should also be the same. Which tells me that, let's see, that should be 1 over x plus 1 over y, right? So that means that g prime of y is 1 over y. I knew that's what you meant.
I wrote it down.
So then g of y will be natural log y. And we're done. The solution is this function y over x plus g of y we figured out was natural log y equals a constant.
So we don't have to find out that constant.
Well, maybe. If they give you an initial condition, then yes. If there's no IVP, then no. All right, so that's the last section.